Thank you. Buenos dias, Chile. It is so great to be here. I am so grateful for this fantastic honor and for the opportunity to be talking to you today about a topic that I absolutely love, and that is super networks. I'll be taking you on a journey in terms of the kind of research that we're doing, and I hope I can inspire you, maybe for collaborations, new friendships, and so on. Now, you may ask, what is super networks? Super networks are networks of networks, and we're all part of super networks. For example, super networks underlie our economies and our societies. You name it. How did you get here today? What mode of transportation did you use? How do you commute to work? How do you go home? There are many, many choices that you make, but the kinds of choices that you make as an individual affects not only you, but affects others. So we are in an era of super networks. Now, not only are congested urban transportation networks super networks, but so are supply chains. Supply chains are used for the production of just about any product around the world. And there will be suppliers in certain parts of the world. There'll be manufacturers that use the supplies for inputs into the production processes. And then there are different modes of transportation, whether by boat or air freight, in which the goods are transported around the world to you and me as consumers. Now, for some of the younger ones in the audience, perhaps the students, your favorite network might actually be a social network. It could be a physical network, face-to-face communications, or virtual communications, for example, as through Facebook or Twitter. Okay? But on these networks, there are different things flowing. When we talk about transportation networks, we have vehicles flowing. When we talk about supply chains, we have products flowing from different origin nodes to different destination nodes. When we have social networks, we have communications back and forth. Okay, also, very, very important in our global economy are financial networks. In 2008 and 2009, we suffered a major financial collapse in the US, which reverberated around the globe. Okay, so it's extremely important for us to be able to model these complex network systems, because something might happen in Chile and it might propagate, globally. Okay, so very, very important. Also, we depend completely on our energy networks, from electric power to renewable energy to even oil pipelines. In those kinds of network systems, you have energy flowing, oil or say electrons. And probably the super network par excellence is the internet. When the internet goes down, I'm sure you all suffer, right? Because the internet is actually interrelated and interconnected with the other network systems. When the internet goes down, it affects our transportation and logistical networks, it affects our energy networks, as well as our financial networks. So it's very, very important for us to be able to model these complex network systems and the relationships among them. So here, lately I've been doing a great deal of work on supply chains because they're fascinating. And also there's a lot of discussion in the world in terms of policies. You're probably hearing about tariffs. You're probably hearing about quotas. Well, what happens if there's a tariff imposed on a particular product? What will that do to the flow of goods? What will it do in terms of the prices? But there are many different decision makers involved in supply chains. There isn't a central controller. You will have manufacturers dealing with retailers, dealing with freight service providers, and so forth. So to make these supply chain networks work, you have to have coordination and communication as the goods flow. And also you need the right payments in terms of the prices and so on. So here, almost pick your favorite product. Is it your smartphone? Okay, is it fashion? Okay, whether we're dealing with, for example, energy networks, or what about food? Food is also part of a supply chain. In fact, a fascinating supply chain because we're dealing with perishable product supply chains. And for example, consumers in the US, they demand fresh produce all year. So now in the wintertime, we're enjoying produce from Chile. Okay? But think about the different modes of transportation that are used, and how you take care of your fruit and so forth will depend upon the quality when it actually arrives at the destination. Okay, also, when you deal with these kinds of network systems, you have to figure out how to optimize. What are the criteria that we deal with? In some, you might really want to say maximize efficiency. Say some producers might want to maximize profits. If you're shipping in a dangerous part of the world, you might want to also minimize risk. But it's also very important to realize that it's not always just about profits. We might care about environmental impacts and sustainability. And also, we're doing a lot of work in terms of disaster supply chains and disaster management. And Chile has some amazing records of success in terms of responding, for example, to earthquakes and also the coal miners. And you should be congratulated. And there, when we come to disaster supply chains, you need to get the water, the medicine, the shelter, the relief items within 2 or 3 days. And the infrastructure might be totally destroyed. The roads are impassable. Communications are suffering. You might not be able to communicate. So it's really, really important to be able to design robust supply chain networks to even respond in the case of disasters. And their time is a critical component. So I am a mathematician, applied mathematician, operations researcher, network scientist, and I love to abstract these very complex phenomena in a way that is accessible to more people. And I do that through the network prism. So I will draw network models. They are pictures, for example. Networks consist of nodes and links, but I also care about flows. Where are the goods coming from? Where are they going? What will that do to the links and so forth? Okay? What happens if a node is destroyed? What happens if you add another road or another bridge? Will that help society or maybe not? I'll be sharing with you a fascinating paradox which emphasizes why you really need to do appropriate mathematical modeling. Otherwise, you might have very bad decisions made for society. Okay? So I use optimization. I also use game theory, a la John Nash, because in many of these network systems, there isn't just one person controlling everything. There are many interacting decision makers and agents, so you have to make sense of that. Some might be competing, some might be cooperating. Okay, so what should we prescribe? Okay, so here, just about all these different kinds of problems you can visualize as a network where you will have different nodes or circles representing origin points, destination points, or maybe points of transshipment. And on these links, okay, you can think of roads, you can think of pipelines, you can think of telecommunication links, you're going to have something flowing, okay? So what are the pathways, okay, that the products take? What are the pathways that information takes? Can we improve these network systems so we help both our societies and our economies? So here, this is an example of a supply chain transportation supernetwork where you have goods being produced at different production sites. You have distribution centers then, where the goods are sorted and get ready for transportation to consumers around the world. But these supply chain networks depend on transportation infrastructure. They also depend on financial networks. And through the internet, you get information being exchanged. And sometimes there's information asymmetry, which is another fascinating subject in itself. So what we're dealing with is not just graphs, it's not just nodes connected to other nodes. We care about what's happening on these network systems. And it's imperative that we capture the behavior of users of the network systems. If you could control the network, you might minimize the total cost to society and satisfy the demand. But you probably didn't take the same route to come here as maybe your neighbor did. You probably take a different road to work or maybe mode of transportation than your neighbor or maybe your child and so forth. So it's very, very important that we capture behavior on networks. Now, we are living in a non-linear world. There is congestion in transportation, in logistics, on the internet, and even on many of our electric power generation and distribution networks. So that's another reason it's very, very important to capture behavior. So I will present you now. Think about this. I always collect stories, which is like the worst transportation system in the world. I think some are in Tehran and probably in India. It was delightful to see bicyclists here, electric scooters, and public buses, in addition to transportation vehicles like private cars. So let me present you with the very, very famous Bryce paradox. And the Bryce paradox occurs not only in transportation networks, but also on the internet. And this has to do with user optimizing behavior. Each of you is trying to determine your best route to get to work, or to come to the Futures Congress today. So here, say you start with the origin node 1, and you're trying to get to destination node 4. There are two choices that travelers can take. They can take path 1, consisting of links A and C. They can take path 2, consisting of links B and D. Say the travel demand is 6 vehicles per unit time. And we assume rational users. So you're trying to get to work as fast as possible, or the Futures Congress. If you take path P1, you will have costs of 10 FA, where FA is the volume of traffic. Link C will be the volume of traffic, FC plus 50. And similarly, you can see the reverse on the second path. So since the structure of the costs on path P1 is similar to the cost on path P2, travelers will distribute themselves so there are 3 vehicles per unit time on path P1, 3 vehicles on path P2, and the travel time will be 83 minutes, whether you're going on path P1 or path P2. Everyone arrives safely. We don't lose anyone in transit. So no one has any incentive to switch. You have user optimization. So this is an example of a decentralized network. Now, let's suppose you're thinking of improving the network for everyone. So let's add another road, which we represent as a link. Say the link E goes from node 2 to node 3. By doing that, you've created another path for all travelers. Path P3 consists of links A, E, and D. The cost, individual cost on link E is the volume of traffic F of E on that link, plus 10. People will find out there's another alternative route. We haven't changed the travel demand. It's still 6 vehicles per unit time. And people keep on switching. It's this Nash equilibrium game until they can't do any better. And look what happens. Before, it took 83 minutes for travelers to get to work. Now you've given them another choice or alternative, and the travel time goes up for everyone. You will have 2 vehicles per unit time on path P1, 2 on path P2, 2 using the new road, okay? Sums up to 6, 2 plus 2 plus 2 is 6. But it's worse for everyone in the network. Before it took 83 minutes, now it takes 92 minutes without a change in demand. So this famous Bryce paradox emphasizes that you have to capture the behavior of users of networks, because you might be adding links thinking that it will improve everything for society, but actually you are worse off. Now you might think, okay, who is this Professor Bryce? This is Professor Dietrich Bryce. He wrote his famous paper and paradox many years ago, over 50 years ago, 1968. But it was in German, okay? And many scientists, including computer scientists, were fascinated by this article. So he came to me and said, Anna, we have to translate this article from German to English. And in fact, he got the idea for the Bryce paradox by sitting in an audience, kind of like this, listening to a speaker, and said, I think I will change things a little bit. Okay? And he had a paradox named after him. So we translated the article. It appeared in the top transportation journal. And I did it also with a doctoral student of mine who happened to be from Austria, Tina Wackelbinger, who's now a very well-established professor at the Vienna University of Economics and Business. So now, what about the real world? Where can the Bryce paradox happen? Okay, it happened in Stuttgart, Germany in 1969, where they actually removed the road downtown, and travel time improved for travelers. Okay? Also, Earth Day in New York City, 1990, 42nd Street was closed to traffic, and the travel time improved. One of the most famous examples is in Seoul, Korea. There was a main superhighway downtown with 6 lanes. It was always congested. There was a lot of pollution. They removed the link, and travel time improved. Okay? And actually, the government got applauded for doing that. So you have to be very careful how you design network systems. If you don't include the behavior of users, you can find very unusual things happening. Okay? So always building more roads can actually add to travel time. So be cautious. So Bryce also now in New York City. The former mayor of New York City, Mayor Bloomberg, did something that was almost like anarchy. He said, let's convert part of Broadway from 42nd Street to 47th Street to a pedestrian plaza. Some people said, wait, this is not Europe. Okay? And it happened. At first, the people didn't like the chairs that he put. They were kind of cheap plastic chairs. And you can see kind of the topology. So this is an interview that I did for a public broadcasting, actually, a TV show, America Revealed. And the gentleman who interviewed me is the winner of the game, a TV show, Survivor. It was March, it was 20 degrees, it was freezing, but it was really, really fun. Okay, so other networks that behave in a similar manner to congested urban transportation networks, the internet, and also electric power networks. Now let me go to the internet. Okay, can you imagine life without the internet? Okay, it has totally transformed the way we conduct business, the way we interact socially, the way we seek out entertainment. And in different parts of the world, you have different levels of penetration. It's interesting to see that now we have more than half of the world's population actually having internet access, which is fantastic. Okay? But what if you could envision an entirely new internet? Okay, maybe all of you are very happy with the existing internet. A few years ago, the National Science Foundation in the United States started a program in which they asked different researchers to try and envision an entirely different internet. What would it have? What kind of aspects? What kind of components? You might be very happy with the content provided, okay, on the internet. We were actually looking at the insides, the network architecture. So this involved me working with electrical and computer engineers, okay, and also computer scientists in a major project. We were one of only 5 teams selected in the US for this future internet architecture project. So what do we foresee, okay, in terms of a better internet? Okay, now we don't have really competition. You really don't know what's happening. You send out a message. It might be hard for you to figure out the route that the messages take. There's a lot of excess capacity in certain parts of the internet, whereas in other parts, there's a lot of congestion. In the US, typically after 6 p.m. in the evening, many people, like more than half, are accessing Netflix and movies, and that tends to slow down the internet. So could we have better pathways, for example? See, so also, there's no kind of economics within the network architecture, okay? There's no competition, okay? So we argue you need more competition, you need more innovation. So that is our prescription. And also, we would like to have different contracts in terms of network service providers. We don't want to be stuck for a year or 2 with a particular network service provider. What if you just want, 5 minutes or an hour and so forth, okay? We also would like enhanced privacy, environmental impact reduction, and very important to have transparency, okay? What's happening with your messages? How are the messages being routed and so on? So we want to encourage different kind of alternatives. We want consumers to also be innovators and people to vote with their wallet. If you like the service that you've gotten from your service provider, we will let that be known, okay, through advertising and so forth, okay? We think that's really, really important. Know what happened, innovate, okay? So entirely new economic relationships will be now possible. And for example, you might be sitting in your favorite coffee shop in Santiago, and maybe you just want to pay for maybe half an hour of service to read your favorite magazine and so forth. That will be enabled, okay, which we think is really, really good. Now you might say, okay, we're happy with the internet already. Why do we need new architectural designs? I don't really care, okay? Well, just a few months ago, there was a new book published by MIT Press by one of the developers of the internet. That's Dr. David Clark. And in the book, which is, designing an internet, he speaks of when they designed the internet, they didn't care about cybersecurity. That was not an issue. Privacy was not an issue. They really cared about communications. So in the book, actually, he singles out our research. Okay, and I find that extremely complimentary. When you try and push the frontiers, get a group of collaborators together, another kind of social scientific network, and then you're recognized by someone who was there in the 1960s. Okay, so when we deal with these kinds of models, we also do mathematical abstractions, which enable us to do a lot of sensitivity analysis. We care about quality competition in content, quality competition in terms of also the network provision and the transport layer. And we also care about the different prices, because to enable transparency and all these different kinds of innovations, people need to get paid. You know, producers, consumers, okay, you need to know what are the prices that are flowing, you know, the level of messages and congestion, and also quality. So networks can take you on an amazing journey from transportation and logistics and supply chains to envisioning a new kind of internet. Okay, I think it's the most fascinating area you can work in, and it's extremely multidisciplinary, which is really, really wonderful. So here, I urge you, if you have a chance and interest, in 2001, I established the Virtual Center for Supernetworks at the Isenberg School of Management at the University of Massachusetts Amherst. And we have collaborators and center associates from around the globe, none from Chile yet. There are many, many talks, presentation, papers, videos, and so on. So I welcome you to actually visit it. And muchas gracias por la atención. Bye. Gracias.